Hello guys, and welcome back to my channel Civil Construction and Tutor, and in this video I'll show you how to design an isolated footing with sloping depth. So basically the condition where the sloping footing is provided is when the gross depth of the footing is subsequently higher and there is no bar provided at the top, and considering the bending moment and shear force is maximum at the face of column or near of the face of the column, that is, there is no shear force or bending moment at the edge. Hence the slope or the depth of the footing is reduced linearly towards the edge, considering that the excess concrete can reduce the cost of the footing. Now let us go to the question. Design an isolated footing for an column 300 mm by 300 mm subjected to an axial load of an 1200 kN. The bearing capacity of the soil is 150 kN per meter square. Take M20 grade of concrete and Fe 415 steel. So the given condition are FCK, that is the characteristic strength of the concrete, 20 Newton per mm square. Yield strength of steel is 400 Newton per mm square. BC into DC, width and depth of column 300 by 300. Service load is 1200 kN and soil bearing capacity is 150 kN per meter square. So the very first thing is to find the area required for the footing. Considering the self weight of footing, 10% of service load will be added to the load. So area required equal to 1.1 times of PU by soil bearing capacity. This gives 8.8 meter square, which is the required length area of the footing. And considering a square footing, that is, we will provide footing in respect to the dimension of column, ratio of width and depth of column. So square footing will be provided, and for area is equal to LF into BF. LF square is equal to 8.8, so we'll get LF is equal to BF as 2.97, and rounding of the value will get LF as 3 meter and BF as 3 meter. So the area provided will be 9 meter square, which is greater than that of the area required. So LF is 3 meter. Similarly, BF is equal to 3 meter, and the length of the overhang in both direction will be same as it is a square footing. So L is equal to basically the length of the overhang, and this is equal to LF minus BC divided by 2, 1.35 meter. Now we are providing a sloping footing, that is, the depth of the footing will vary towards the face of the column from the edge. So mathematically there is no moment and bending or shear force at the edge of the footing, so the depth here should be minimum of the total depth provided. But for general practice, the minimum edge depth should be 150 mm for the isolated footing. So we'll provide edge depth D naught as 150 mm, but for our case we'll take D naught as 200 mm, considering the depth of the footing is much more greater than that of the normal case, as the load is greater, that is 1200 kN. So we'll provide D naught as 200 mm. And similarly, for erecting the formworks for casting column, we'll provide offset of 100 mm, so that it will be much more easier to work in the site. So these are the things that you have to consider while designing the sloping footing. So the second step is to compute upward pressure on footing, that is the soil pressure due to the resting of the footing on the soil. So sigma, that is the pressure, is equal to PD by A plus mu by Z. So mu, here there is no moment or eccentricity, so this will be is equal to 0, and PD is basically design load, so factor of safety 1.5 into 1.1 as the service load of footing weight into 1200, which is the service load, divided by the area provided, and this comes as 220 kN per meter square. So sigma is equal to 220 kN per meter square, and this should not be greater than 1.5 times of soil bearing capacity. So this will be 225, which is less than the maximum or factored soil pressure on footing. Third step is to check for bending. and the critical section for bending lies at the face of column, so considering overhang portion as a cantilever beam. So that basically means the soil pressure under this area is responsible for causing the moment about the axis YY. So as we know, this portion, or we can say the critical section, is at the face of the column. So now this can be considered as a cantilever beam subjected to an UDL, and the UDL is equal to the soil pressure, and as it is in per meter square, so we have to convert this into per meter, for which we will distribute this soil pressure along the width of the footing. So length of the cantilever portion, as I have said, L, this is 1.35. resisting width, so this is the difference between the pad footing and sloped footing. So in case of the pad footing, the whole width of the section is responsible or is available for resisting the moment, but for our case, that is the sloping surface, the resisting width will not be the width of the footing, because as the moment is maximum at the face of the column, so the width available at this particular section will be the resisting width, and for our case it is equal to DC. So we are considering this length LF, so the resisting width will be equal to DC plus 2 times of offset. Okay, you are getting my point. DC and BC are equal to, so you can write as BC, so BC plus 2 times of the offset provided. So this is the width that is responsible for resisting the bending moment. So B dash is equal to BC plus 2 times of offset, and the width is of the column is 300 mm, so 0.3 meter plus 2 into providing 100 mm offset, we get this as 0.1, so 2 into 0.1, so finally 0.5 meter, 500 mm is the resisting width. But in general case, for a rectangular footing, it would have been the length or width of the footing. And now UDL along the width of the footing, as I said, this is in per meter square, we'll convert this in per meter, so sigma into BF, so it will be distributed throughout the width of the footing. So sigma, which is 220, into BF, width of the footing is 3, so this comes as 660 kilonewton per meter. Now bending moment for a UDL subjected to a cantilever beam, the bending moment is, so if the UDL is P, then P into span of UDL being L into L by 2 being the center of the UDL. So finally we get bending moment as UDL into L square by 2, so L being the length of the projection, which is 1.35, 660 into 1.35 square by 2, so this comes as 601.425 kilonewton meter. So this is the maximum bending moment. Now we have to calculate the depth according to the bending moment. You can also calculate the depth according to the shear, one-way shear, but it will be but in case of the sloping footing, as we are calculating the bending moment with the resisting width as the value BC plus 2 times offset, so the depth calculated from the bending will be much more adequate in comparison to the bending in comparison to the value calculated from the one-way shear. And the difference between the depth calculated from bending and the one-way shear is that from the one-way shear the area of concrete will be more, and the value of depth computed from bending gives more percentage of steel. So that is the particular difference between calculation of depth from bending and calculation of depth from one-way shear. So for depth according to bending moment, SP16 table C gives us this value for FE415. Mu by FCK BD square is equal to 0.138. So this is the limiting moment resistance index, 0.138, and we'll compute the value of D from this equation. So cross multiplying the terms, we get D required square is equal to 601.43. this is the maximum moment converting into Newton mm, and 0.138 FCK 20, and resisting width is 500. Don't get confused with the value of B. D required is equal to 660.13. So this is the depth required according to the bending moment consideration, and we'll provide a value slightly greater than that of the value computed. So we'll provide D as 694 mm. Don't get confused, we will not provide twice the value for this case, that is the sloping footing. In this case, the moment computed depth computed from the bending moment is much more adequate. So 694 mm. And if you consider the flexible criteria of the footing, then you can increase the depth required by 4/3 times of the computed value. The bending moment in the other direction is also same, because the projection is same as it is a square footing, and hence but the effective depth will be different in the other direction. If you see here, so I am computing the bending moment along this direction, so the effective depth will be so for now the effective depth is equal to overall depth minus clear cover minus the whole bar minus half of this longitudinal bar. And if I compute along this direction BF, then it will be capital D minus clear cover minus longitudinal bar will be at the bottom, so it will be D minus clear cover minus 5/2. So that is the effective depth will be different, that is 12 mm greater, considering that I am providing 12 mm bar in both direction. Hence the area of steel computed with the depth greater will be less, hence we will compute the area of steel considering the smaller depth. So calculation of reinforcement from IS 456/2000 Annex G clause G 1.1.c, we have Mmax is equal to 0.87 FYAST into D 1 minus FYAST FCK into B dash into D. Don't get confused with B, as I have already said this is the resisting width. So substitute the value. We have maximum bending moment as 601.43, converting this into Newton mm. 0.87 415 into area of steel has to be computed, and similarly depth provided is 694 and other terms remain same. Don't get confused with the value of B dash, that is the resisting width 500. So area of steel is computed as 2906 mm square, and the percentage of steel provided is area of steel divided by B dash into D into 100. Area of steel 2906, B dash 500, D is 694, so this comes as 0.83%, and the minimum area of steel to be provided is 0.12% of the concrete area. And as we have a sloping footing, so the value of D is different here, it will be D average. So we will take the capital D average of the gross depth and the edge depth, and as we have provided D as 694, and then D will be equal to 694 plus clear cover plus 5 plus 5/2, 762 mm, and another depth will be equal to 762 plus minus clear cover minus 5/2, and if we put this value 762 plus 200/2, this comes as 1710 mm square, and the provided steel is greater than that of the required one or the minimum area criteria, so it is okay. Assuming the resisting width as B dash 500 mm and D as 694 mm, the reinforcement required is calculated. So we have calculated the reinforcement considering these two conditions. Now this reinforcement will be provided or distributed over the entire width. So this is how the reinforcement distribution is done for the sloping footing. And assuming phi as 12 mm, spacing required is equal to width of section divided by area of steel required divided by area of rebar. I have explained this in my previous video also, so I won't spare my time on this. So the width of the section is 3000, not resisting width. We will put the width of the section as we are distributing the reinforcement, divided by area of steel provided 2906 pi by 4 into 12 square So this comes as 116.65 mm. So just converting into the multiple of 25 so that it will be easier to work on site, it will be 100 mm. So providing 12 mm bar at 100 mm spacing. So let me calculate the number of bar as well, so it will be easier to understand. So the number of bar is calculated by using this formula: width of the section divided by spacing provided plus 1. It is plus 1. So width of the section, so we have to reduce the clear cover on either side. So if this is 3000, we have to provide cover at both ends. So 3000 minus 100 divided by 100, that is the spacing provided, plus 1. So this comes as 13 number. So the 13 number of bars should be distributed along the width of the section. So provide 30 number of 12 mm bar at 100 mm center to center in both axes, in both direction. Now area of steel provided, as we have increased the spacing, that is we have spacing was computed as 116, but we have provided 100 mm, so the closed spacing has been provided. So the area of steel will be different now. 30 into as the number of bar into the area of rebar provided. So 3390 mm square, which is greater than that of the area of steel required. It is okay. Now this is the reinforcement drawing. As you can see on the plan, we are providing 12 mm bar at 125 mm along LF. Similarly 12 mm bar at 125 mm in this direction as well. So that means this bar is placed parallel to shorter, or there is no shorter side, parallel to B, and this is placed parallel to L. So this is how you can understand. And in section also you can see 12 mm bar at 125 mm center to center. Similarly the clear effective depth along this direction is 694 mm and the gross depth is 762. So it is 762. This is 200 mm, that is the edge depth, and offset is provided as 100 mm. And similarly 8 number of 16 mm bar is coming from the column. This is an approximation, or we can say this is just a general concept. The question has not given the number and size of rebar, just I have assumed 8 number of 16 mm bar. It is required to calculate the development length required for footing, for the column bar into the footing. Now the next step is to check for one-way shear. The critical section is at distance D from face of the column. This is applicable for both uniform as well as sloping footing. So as the depth is 694 mm and the resisting width, for now it will be B dash is equal to DC plus do into D. So the resisting width will be equal to depth of column plus 2 times of D, that is, okay, let me draw. So assume this is a square footing, okay, this is square, and considering this as the column, and we are resisting width in this direction, that means depth of column plus D, that is the depth of foundation. So this will be the resisting width for one-way shear. 1688 mm, DC being 0.3 and this being, okay, 300 mm plus 2 into 694, 1688 mm. As the pressure distribution of soil is uniform, so the pressure at any point will be 220. So sigma D is equal to, at a distance D, it is 220 kilonewton per meter square. And shear force is equal to, for a cantilever section, I have done this before also, so for a shear force it is equal to, considering this is P kilonewton per meter and span is L, shear force is P into L, and for a particular point at a distance D it will be P into L minus D. So we are using the same concept. 660 into L, that is the length of the, considering this DC, okay, 1.35 minus 0.694, so this comes as 433 kilonewton. This is the shear force acting. For this shear force we have to calculate the depth, that is, for a sloping footing the depth is different. At a distance d the depth is different, and that what makes the computation different than that of the regular pad footing. So we have to find the depth at the critical section. So at a distance d the depth will be, effective depth will be this height or this magnitude. So we have to find this, and for this we have to use triangular law, that is the similar triangle concept. So if we see here, this will be the value d naught being edge depth minus clear cover minus 1 bar minus half of the bar. So we will get the effective edge depth. We can say this term as effective edge depth, and for remaining this magnitude we have to use this similar triangle rule, and there is an offset, so the triangle will start from this point, and the height of this triangle is d minus d naught, okay, d minus d naught divided by length of this triangle, which is length of projection minus offset, so 1315 minus 100 into length of this triangle, which is L minus D. So if you can see L minus D. Now substitute the value, we will get the depth at critical section, this depth D1 as 421 mm. So this is the depth at the critical section, and we have to check whether this depth is sufficient for resisting the shear. Another difference is for calculating the shear stress. For a regular beam or for a rectangular beam we have computed shear stress as VU by BD, but for a varying depth the shear stress is computed with this formula as per IS 456 2000 clause 40.1.1. So tau V is equal to VU plus minus MU by D one way, that is the depth at critical section, into tan beta divided by B into D one way. So VU being the shear force, MU being the moment at the critical section, D1 being the depth at the critical section, tan beta is nothing but this beta, okay, so tan beta is equal to, we have to find this. Similarly B is the resisting width, so we'll find tan beta. So tan beta is the, we can use this triangle, so D minus D naught divided by L minus offset, so we'll get 0.44. Similarly MU is the moment at critical section. For a UDL, for a cantilever beam subjected to UDL, moment is computed as P into L by 2. So UDL is 660, we have already computed, 660 into L minus D, that is, for now the length of the or span of the beam is L minus D, because we are finding at the critical section, so L minus D divided by 2, so this comes as 142.1 kilonewton meter. So now we substitute the value. Tau V is equal to VU minus, as we have plus minus sign, for our case as the code says, the moment increases numerically towards the end, fixed end, or we can say if the moment and depth increases in the same direction numerically, then we have to provide a negative value. So in this case the moment increases towards the direction where depth increases, so we'll take negative sign. V is 432 minus MU is 142 divided by D one way, 1 so 0.421 into 0.44 tan beta divided by 1688, that is the resisting weight, into 0.421, so this comes as 401 kilonewton per meter square. And this is in terms of kilonewton per meter square. We have to convert this into newton per mm square, so this comes as 0.4 newton per mm square. And for computing the shear strength of footing, we will use the percentage of steel and the grade of concrete. So percentage of steel provided for one way shear is equal to area of steel provided divided by B dash into D into 100%. So we are checking whether the area of steel considering the section for one way shear is sufficient or not. And for this, area of steel provided that we computed was 3390 by resisting width is 1688 and the depth at critical section is 421, so this comes as 0.478 percentage. And for P percent 0.478 and M20 grade of concrete, using table 19 of IS 456-2000, we get shear strength as 0.47 newton per mm square, and the maximum shear is 0.4. So if we compare this to value, we find that it is safe for one way shear. Similarly, check for two way shear. The critical section is at distance d by 2 for two way shear, and it is 694 divided by 2 is equal to 347 mm from the face of the column. And at the face of the column, at a distance d by 2, the shear stress, the soil pressure is 220 kilonewton per meter square, considering a uniform distribution of soil pressure. And that means at a distance d by 2, so if we see in the plan, and from this also d by 2, so we get a rectangular, or it could be a square section, and this section is responsible for resisting the two-way shear, that is the punching effect of column, that is the column should not penetrate into the footing, and for ensuring this condition, the depth should be adequate for resisting the two-way shear. And this section is resisting section, so the resisting perimeter is equal to 2 times, that is for a rectangle it is 2L plus B, so 2 into L being BC plus D by 2. Similarly, in this direction BC, or you can say DC plus D by 2 plus D by 2, as both are equal, so you will substitute the value and you will get 4000 mm. Similarly, area of concrete resisting punching. Now the area of concrete resisting the punching is this much portion. So for this we have to find the area of concrete resisting punching. We have to find depth resisting two-way shear, that is at a distance d by 2. So the depth at distance d by 2 has to be computed. So we have to compute this value, that is effective depth for two-way, and it is nothing but again the same concept of using the triangular rule. Only the difference will be we have to add minus d by 2 instead of d. So while calculating for one-way shear, all the value are same, the only difference is that we will add d by 2 for two-way shear. Okay, so we get this value as 573.3 mm, and shear force is equal to sigma d by 2 into area of unhashed section. So for calculating the punching shear, we have to find the area of unhashed section, that is this is the unhashed area. So here the unhashed area is the tributary area for the two-way shear, that is the load which is responsible for causing the two-way shear, as the load acting from this area causes the diagonal crack from the face of the column, and it can be computed by area of footing minus area of concrete resisting section. So we can get this, and for the area of footing it is LF into BF. Similarly, area of this section is BC plus D by 2 plus D by 2 dc plus d by 2 plus d by 2. So we can get the value of shear force as 1765.2 kilonewton. So this is the shear force, and shear stress is equal to tau max. So now for shear stress, it is V by area of resisting section, and the shearing punching shear is 1762.2. Converting this into Newton, 10 to the power 3, divided by area of resisting section is perimeter into depth of section considering the two-way shear. So d2 that we have computed as 573.3. So this comes at 0.75 Newton per mm square. So this is the maximum shear stress. Now according to IS 456 2000 clause 31.6.3.1, the shear strength of concrete is Ks into tau c. So the value should not exceed this, else shear reinforcement has to be provided, which may be an expensive thing to do. So we'll just consider this. So this is from the code, and beta being the ratio of longer to shorter dimension of column. So 0.5 plus 300 by 300, 1.5, and this value should not be greater than 1. So we'll take K as 1. So K is 1 and tau C is 0.25 under root FCK. So this comes as 1.118 Newton per mm square. And since tau V is equal to K tau C, so 1 into 1.118, so this comes as 1.118 Newton per mm square. That is the shear strength of concrete. Since the maximum shear stress is less than that of the shear strength of concrete, so it is safe against two-way shear. Now check for development length. This is according to IS 456 2000 clause 26.2.1. So LD, that is the development length, is equal to phi into sigma s divided by 4 into tau BD. So as I said, the column or the bar coming from column is of diameter 16, so phi is 16 into sigma s being the stress at the service load or design load, so 0.87 into 415. This is the load that we'll consider for the stress considered for the service load. 4 into 1.2 into 1.6, so tau BD is the design bond stress. For M20 concrete it is 1.2, and considering a deformed bar it is taken as 60% in, or the increase in 60%, so 1.6. so this comes as 752 mm, and the available length is, so here you can see the projection is of 1.35 meter. We'll give a clear cover at this end and we'll provide a clear cover at this end as well. So the available horizontal length will be equal to 1.35 plus 0.05 minus 0.05. So it will cancel out, and finally the available length will be 1.35 meter, that is 1350 mm, and the required length is 752. So the available length is sufficient for development length. Now the last step is to check for the transfer of force to column and footing, that is the force coming from column into the footing. This is from IS 456 2000 clause 34.4. The design force to be transferred into the footing is 1.5 times of the service load coming from the column. So this is 1800 kilonewton, and the bearing stress of column is nothing but 1.5, that is the design load, divided by area of column, 20 Newton per mm square. Area of column 300 by 300, and bearing capacity of concrete is 0.45 FCK multiplied by under root A1 by A2. So I have already explained about A1 and A2 in the previous video. In this video I will not go on detailing about that thing because column face governs the strength, so we will not need the term A1 and A2 anyway. For column face the value of A1 and A2 should be taken as 1, and for other phase the value of A1 and A2 should not exceed 2, and for the bearing capacity we'll take the smaller value, that is we'll consider the least bearing capacity of concrete, that is for the column face, so 0.45 FCK into 1, that is the bearing strength of concrete. So now we'll calculate the force that will be transferred through the bearing, that is the column and footing interface. So that will be equal to 0.45 FCK under root A1 by A2 into area of column or pedestal, anyway So 0.45 into 20 into 1 for the column face into 300 into 300, that is the area of column base. So this comes as 810 kilonewton. So what we have to understand is that the force that can be transmitted from column to footing through the bearing, that is the column and footing interface, is 810 kilonewton, but the force that has to be transferred is 1800 kilonewton. So we have to provide additional arrangement to transfer this load into the footing. So according to IS 456-2000 clause 34.4.1, if there is any unbalanced force, that is if the bearing strength of the concrete is not sufficient to transfer the force, then the reinforcement has to be added to transfer the force into the footing, and hence we will do the same thing, that is the unbalanced force has to be transferred through reinforcement extension into the footing, either via extension of the longitudinal bar of the column or dowel bar. So I have already explained about calculating the reinforcement for dowel bar if we don't want to extend the longitudinal bars into the column. You can find that in my other videos. But for the easiness, generally the bar from the column is extended into the footing up to the LD required to transfer the unbalanced force. So this is how the design of isolated footing with sloping depth is done. I hope it helped you. So you can see here, this will be the LD, this length, and the reinforcement, that is 8 number of 16 mm column bar, is extended up to LD into the footing to ensure the transfer of the load from column to footing. Thank you.